All right, working another one of these sample problems. This one's from chapter 12. It's problem number 38 at the end of the chapter if you're following along. What this problem involves is the calculation of the heat of hydration for lithium chloride and sodium chloride. We want to know which cation has a stronger ion dipole force with water based on some data that were given, and try to answer why that trend is reflected in the data, okay? So if we look closely at our information, we see we have two compounds, sodium chloride, lithium chloride. So starting off, we see we have the same anion, or negatively charged ions, CO minus 1, CO minus 1. Of course, that's called chloride. That's our anion, the negative ion. But we have different cations. Cations with positive ions, sodium plus 1 and lithium plus 1. They're both in group 1 of the periodic table, carry a plus 1 charge in their ionic compounds. But, of course, they're different elements. They might have different behaviors, and in fact, we'll show that they do upon hydration in water. We're also given lattice energies in kilojoules per mole for both compound. Lastly, we're given the delta H solution in kilojoules per mole for both compounds to go into aqueous solution. So just right off the bat, I think what tends to be most difficult for problems like this is just to have a good idea for what all these terms mean. Like lattice energy and enthalpy of solution, and there's another one up here, right? I mean, we need heat of hydration or enthalpy of hydration. So what do all these terms really mean? And keeping track of that's probably the hardest part for getting these types of questions right. So I hope to impress upon you that business here as we work this problem. However, before we get into that, I wanted to make sure everyone's on the same page in determining whether or not processes are endothermic or exothermic. And specifically, that discussion is going to revolve around these numbers here for delta H solution. This is our enthalpy of solution. So the enthalpy of solution in kilojoules per mole here is the net enthalpy change when our material is basically hydrated into water. So it accounts for both of the energy intensive steps where we have to break the solid apart and also create holes in our solvent. This is basically accounting for both of those, the net change in energy. So it's basically going to correspond to whether or not our beaker is going to get cold or warm when we dissolve our ionic compound in it. Okay, now looking at the sign on the first one, the lithium chloride, it's a negative 37 kilojoules per mole. That, of course, the fact that it's a negative value corresponds to an exothermic dissolution process. The second one, though, is endothermic because by virtue of the positive sign. Okay, so this beaker is endothermic. This beaker would get cold for this endothermic system. The other one might warm up a little bit if you start to dissolve some lithium chloride because it's an exothermic process. Exothermic processes give off heat. Endothermic processes absorb heat from the surroundings, and that's what differentiates the two, okay? So that's the net outcome. Let's talk about, though, how we can figure out this heat of hydration bit and a little bit more about, lattice energy and this net enthalpy change. And I think once I draw a figure here for each of these ionic compounds, things will make a little bit more sense, okay? At least I hope they will. Now, recall that for these ionic compounds, one thing we did is to draw a figure that looks something like this. And we said for any ionic compound, there is going to be a huge energy cost that's associated with breaking up the ions that form the ionic compound. It's because these ionic compounds consist of positively charged ions mixed with these negatively charged ions. They're packed and arranged in a very precise fashion with the ions very close together. And of course, we know that opposite charges attract. So ionic bonding is very, very strong. That compound is held together by these very strong forces. And if we're going to take this stuff and dissolve it in water, we're going to have to break apart those ions. They're going to have to separate from one another. That's going to be a huge energy price to pay. Okay? So one of the steps always that is involved in dissolution of an ionic compound is a hugely endothermic step that requires a very, very large amount of energy. That's akin to breaking up the solute. Okay? That was one of the steps in our solution formation that we talked about in lecture. We gave that one term delta H solute, you may remember. Okay, delta H, this is a triangle. Delta H solute. Now, for ionic compounds, we use this business of lattice energy to help guide us to predict how big of an energy cost will be required. And to make a long story short, delta H solute is just equal to the negative of the lattice energy. Now, the reason why that is, why this is a nice proxy of this, is the way lattice energy is defined. Remember, lattice energy is the energy, it's always exothermic, okay? It's the energy you get back when a mole of the ionic compound combines from gas phase ions to form the solid. So it's a purely hypothetical thing. We're not going to do this experiment in lab. I mean, think about having 1 mole of each gas phase ion and then combining them just to make the crystalline structure 1 mole of it. It's not something we're going to do in the lab. It's kind of a hypothetical construct. But this tells us how much energy we get back when that process happens, right? The gas phase ions combine to form a mole of the compound, the ionic compound. Always hugely exothermic because we get lots and lots of energy back when these ions get very, very close together. So that's the lattice energy. The negative of that, or it multiplied by -1, tells us this energy price that we have to pay to break apart our solute molecules, okay? Now, in the case of the first salt, the lithium chloride, that would then be equal to 834 kilojoule per mole. Okay. Now, once we break apart the ions, we can then dissolve them in water or hydrate them. Okay. Now, looking at this number, being a -37, I know I can draw a down arrow, meaning we move lower in energy. Okay, lower in energy. That step corresponds to the formation of new intermolecular forces between the ions in the salt and water. Remember, water is a polar solvent and it likes to interact with ions such as Li+1 or Cl-, okay? This down arrow is the formation of new ion forces with H2O. That's what it's representative of, okay? And you may remember from our discussion that entire arrow is referred to as the enthalpy of hydration, and the heat of hydration. So when it's asking us to compute the heat of hydration in the problem, it's asking us for computation of that. Okay? Now you might be tempted to say, oh, it's 834. It's not. It's not. Because the length of these arrows are not equal. Okay? And how did I know that? Well, my delta H solution was not equal. Okay, so what I'm getting at here then is this distance between where we start before the ions were broken up and where we finish, which is down here after the solution is formed. This gap right here is that delta H solution. That is our enthalpy of solution. So in this particular case, for our lithium chloride, that gap corresponds to 37 kilojoules per mole. Our energy is lower when we finish, so the net change is negative. It's an exothermic process. Okay, that's where we finish. All right. So after I draw this figure, then it becomes a little bit easier to figure out how I can compute this delta H hydration with the length of that arrow. Because now I see I have to bridge this gap, the 834, to break the ions apart. And I also have to bridge this gap. So this arrow is simply the sum of the two. So in this particular case, that's delta H hydration for lithium chloride is equal to 834 plus 37 kilojoules per mole. And if you do the math on that, you get 871 kilojoule per mole. So that's the answer for lithium chloride. We can then turn our attention to sodium chloride. A very similar figure will be helpful. This is our starting point, where we've got our 1 mole of solute. We have to create holes in the solute, or break it apart basically. Okay, that's going to be an energy price. Again, that is, your book refers to that as delta H solute, which is quantitatively equal to -1 times the lattice energy. So this is delta HLE, which stands for the lattice energy. Okay, it's not a very good H, but it's supposed to be an H. Okay, so it's the -1 times the lattice energy. For NaCl, that corresponds to 769 kilojoules per mole. So not quite as large as it was for the lithium chloride, but still a very formidable amount of energy. Now what else do we know about this? Well, we go up to this imaginary level here where the solute ions are separated, and now we're going to basically hydrate them, or add the solute ions in the gas phase back into our water. Again, it's a purely hypothetical process, okay, but we can at least think about modeling it as the enthalpy of hydration. And when we do so, we see that the net process is a little bit endothermic. So that tells me that I can draw my line right about here, okay? This gap between the two, between where we start and where we finish, is equivalent to 3.88 kilojoules per mole, Okay, this is a little bit higher than that. That's typical of the endothermic process. Again, that corresponds to the enthalpy of solution. That's why this enthalpy of solution is always the net change. Always the net change, okay? There it was considerably bigger. It was exothermic process. Here it's going to be an endothermic process, but that net change is always the enthalpy of solution, okay? And we want to know, well, what is this delta H hydration? And again, that's that process where a mole of gas phase ions become hydrated or surrounded by water molecules, become dissolved in water. So what is that enthalpy of hydration? Well, again, it's just whatever is necessary to bridge the gap. This was 769. This was 3.88. Okay, positive. So we're not quite back to where we were. So it makes sense just to do this minus this number. And if we do that, we get 765.12 kilojoules per mole is our enthalpy of hydration. I should also point out that these enthalpy of hydrations are always exothermic. That's one thing I missed before. Okay, so they're really truly a negative 76512 and a negative 871. They're always exothermic. And you say, well, how does that jive with these numbers, right? One being endo, the other being exothermic. Well, keep in mind what we're talking about is different processes, okay? Delta H solute, breaking the ions apart, always endothermic. You always have to pay that huge energy price to break the ions apart. Enthalpy of hydration, by definition, is taking the gas phase ions that result, putting them into water, surrounding them with water molecules. That's always going to be an exothermic step because the ions will want to interact with the polar water molecules. It's a favorable interaction regardless of what ions we're dealing with. It's a favorable interaction, always highly exothermic. This delta H solution, or the enthalpy of solution, is the balance between the two. It's the net change, okay? The net change between these two interactions. In this case, the reaction was 37 kilojoules per mole exothermic. We ended at a lower energy than where we started, okay? Because the intermolecular forces must be very, very strong there to make that happen. In this particular case for sodium chloride, it took more energy to break the ions apart than what we got back through hydration. We got most of it back through hydration, but there was a small gap of 3.88 kilojoules per mole that we couldn't quite get back, okay? So the hydration is always the exothermic process. And this is always endothermic, this is always exothermic, but the overall could go either way, depending on the magnitude of the arrows here and here, okay? In this case, the first arrow was smaller. In this case, the first arrow was bigger. Right? So hopefully that makes a little bit of sense to you. I think if you understand the vocabulary, it's very helpful for getting these types of questions correct. Okay, so the question continues after we get these numbers, which was the first part, heat of hydrations for all these. Which cation has stronger ion dipole forces with water? Okay. Well, what makes sense? So ion dipole forces originate when we hydrate the ion, right? So it's going to basically be in these enthalpy of hydration terms here and here. So which one's bigger? Okay, well, it's this first one. All right, so the lithium chloride is bigger. Now, it's speaking specifically of cations, the positively charged ions. And the reason why we can do that in this case is because both anion is identical. So their interactions with water, it's going to be identical. It doesn't matter if it comes from lithium chloride or sodium chloride. The chloride-water interactions are always the same. But what makes the length of these arrows different then is the interaction of the cation, which is different, either sodium or lithium. And we can see that the delta H hydration for the lithium salt is considerably bigger than it was for the sodium. So that would mean that the ion dipole forces for the lithium salt is considerably stronger than the ion dipole forces for the sodium cation. Okay, so that's the one that the lithium cation's got the stronger ion dipole forces. Now, why is that? Okay, well, if you look at your periodic table of the elements, let me see if I can track one down for you real fast. Look at that. Okay, periodic table of the elements. Break this guy out. Let's see if I can get it close enough to the camera and you can sort of see it here. Okay, and we look over here where we see lithium and sodium, right? Notice that lithium is above sodium on the periodic table. And that corresponds to lithium being a little bit smaller in terms of its ionic radius, okay? Now, the beauty of that, because it has less electrons in its valence, its electron orbitals, okay? And the beauty of that is that the smaller ions can oftentimes form more intense or stronger electrostatic interactions with other materials, such as water in this particular case, okay? And that's going to lead to a more favorable interaction and a more exothermic enthalpy of hydration. And so I hope that this discussion was useful for you. I think when you're studying this section of Chapter 12, the most important thing that you could do was probably two things, okay? The vocabulary terms themselves, understand what heat of hydration corresponds to, understand what lattice energy corresponds to, understand what delta H solute corresponds to. That's breaking up the solute, which is always -1 times the lattice energy, okay? Understand the enthalpy of hydration is the the energy you get back, the exothermic process, that results when you take the gas phase ions and you dissolve them in water, you hydrate them. So the key is getting all this vocabulary down and understanding what these different terms correspond to. And if you can do that, and then if you also have the idea of how to draw one of these figures and understand which processes are endothermic, which processes are exothermic, I think you can go a long way to solving these types of problems, okay? Understanding the physical business behind this material, okay? Thanks.